Okay, yet again, I'm going to be doing another kind of walkthrough continue the walkthrough through our chapter. I'm going to talk to you about problem solving right now, and I'm going to refer to the 3.5, but there's a lot more to it, and that's probably one of the things that we're going to spend the most time with is trying to figure out how to problem solve effectively. Now, they talk about the idea in 3.5 about conceptual problem solving and the difference between memorizing how to do a problem and actually being able to understand how to solve a problem. The analogy they give is if you have someone giving you directions and in the car with you and telling you where to go versus you having to figure out how to get there. It's for me, it's kind of like the GPS syndrome, where I follow everything on my GPS. If I did not have that, I would be completely lost because I could go someplace 15 times and still not know how to get there. So what we want to do here is we always need to kind of work backwards from the problem, see what they're asking us to solve, and then see if we have the tools to apply what we've learned to that problem. Because the AP exam is going to be like that. It's not going to give you a problem where you're like, oh, I've seen that 15 times. You may get lucky and see something you've done before, but they're going to try and have you apply what you've learned to something you've never seen before. So I'm going to kind of fly through this right here. If you take a look in 3.5, they kind of walk through this. It's really worthwhile taking some time and reading it through and talking it through. But just understand this, problem solving will be the central focal point of what we're doing because, again, the AP exam is made up of problems. So the more problems you do, the more familiar you're going to be, and the better you are going to be time-wise in getting to the final end. Now, I'm going to slide over here to something that goes hand in hand with empirical formula. I don't know if you remember last year we did percent by mass and empirical formula, and they're two sides of the same coin. If you know the elements that you have in a compound, you can figure out what percentage each one of them is of that compound. So let's take a look here at 3.6, and I'm going to kind of walk you through this again. So they ask, and I would have started off with something like CO2, right? If I give you CO2, I can be like, I can get the molar mass of carbon, right? And that's 12.01, right? And then I know that I have, for the overall molar mass, don't I have two oxygen, and each of those oxygens are 16.00, right? I'm good to see I'm in horrendous lag right now. So overall, that's going to give me 44.01 grams per mole for the molar mass of carbon dioxide. And then, just like anything, you can figure out a percentage of something else. If I want to figure out what the percentage is of carbon, couldn't I go, oh yeah, I have 12.01, and couldn't I divide that by 44, the overall amount? So carbon's total percentage would be 12.01 divided by 44.01. I can do the same thing using 32, the 2 times 16, to get to 32 divided by 44 to figure out the percentage of carbon. But if there's only two things, then see how we have only a carbon and an oxygen here, and both of these together, when you add up your carbon percentage and your oxygen percentage, they have to equal 100%. Wouldn't you agree with me that once you figure out the percentage of one thing in a compound, you can subtract from 100 to figure out the other thing? So they're just doing that through here, where they're giving you a much uglier compound, C2H5OH, and they're asking you to walk through it, figure out the overall molar mass of 1 mole. And then in order to figure out the percentage of each one, you take that individual thing. Now, they took carbon, and it's really important when you do this. I do it this way, and they can solve it however way they want, but aren't there two carbons making up this as part of this overall 46.07? So you'd have to go 2 times 12 to get to the, and I said 12.01, right? So to get your 24.02, man, this is becoming worse and worse writing-wise. And then you can divide that by 46 to figure out that it's 52.14% carbon. And you can do the same thing for hydrogen, and you can do the same thing for oxygen. The problem at the bottom of the page, where it's interactive example, and they ask you to figure out the mass percent, I'm going to let you guys do that on your own, but it's exactly the same thing. You're going to work through, you're going to take the molar mass from your periodic table, and you're going to divide by the overall molar mass to figure out the percentage of each thing. Now, what's kind of cool about this is that, one, all the individual things have to add up to 100%, or you've done some math wrong. And then two, if you can figure out the mass percentages of each thing, we can go the opposite way to figure out the empirical and molecular formula. So that's a great lead in into the next section, which is 3.7, determining the formula of a compound. Now, the easiest way to think about this is by going backwards from the percentages to figure out the element itself. Now, they give you an example here of working through carbon and carbon dioxide, just like I talked about, and dividing by the molar mass, etc., etc. And they walk you backwards saying, oh, incidentally, you could figure out the amount of one of the things if you knew the overall percentages. Now, I'm not going to go through this section right here, but I encourage you heavily to do this on your own. Now, one of the things that I do want to do is I want to do a practice empirical formula problem with you. And you know what I'm going to do is I'm going to do the opposite. This is going to be, I'm going to set this online as well from one of the older videos I did. But this little problem solving here works really, really well. And the steps kind of go like this. If they give you a percentage of each element in a compound, pretend you have 100 grams and make them into grams. Convert your grams to moles. Once you have your moles, take each mole and divide it by the smallest number mole. Remember, that's a really important step. And then you're going to have the ratios of each one. And you may have to multiply by some factor to get it to a whole number. Now, again, the best way to do this is to actually try doing a problem like this. Now, this problem actually works out really, really well. So I'm going to scroll down here and see if I can find one that does not give us an exact number. So let's do it this one right here along with them. So in this case, you see how they give us 46.34% phosphorus and they give us 56.36% oxygen. Yeah. That's no good for us because we can't do anything with percentages, but we can kind of pretend that we have that number of grams because we make believe that we have 100 grams. So you see how the 43.64 becomes 46.64 grams, and here it becomes 56.36 grams. Now, in every case, grams never help us with this. We always have to convert to moles. So we're going to take the grams here, and we're going to use the molar mass of phosphorus and figure out the moles. Same thing with oxygen. And here's what I want you to be really careful, because often we think, oh yeah, oxygen is O2. And this is problematic because we're actually trying to figure out what is the value of this right down here, X. Now, in reality, it's probably better if I did PXOY. We're trying to figure out these two values right here. So if you in your, I'm going to scratch that out. These are not the droids you're looking for. If you're trying to figure out what this Y is, and when you're doing the molar mass of it, you already put a 2 down here, you're going to end up with a messy problem. So if you take a look here, we end up with 1.490 moles of this and 3.523 moles of this. And the way we try to get to whole numbers is we divide both of these by the smallest number. You see how 1.409 moles is the smallest in both these cases. And what we end up with is 1p for every 2.50. That's actually the ratio. We could write this ratio as P, O, 2.5. But there's a problem with this. We do not want to have half of an atom. So what we do is we find the nearest multiple, the lowest multiple, the whole number, that we can get rid of this and make them whole numbers. And you can start by going times 2, times 3, times 4, times 5, until you get to whole numbers. In this case, you can probably observe that if you multiply both of these by 2, you're going to end up with P2O5. Okay, so the other thing they're going to ask you to do quite often is not just figure out the empirical formula, but the molecular formula. Now, what you need to understand is the molecular formula, a molecular formula, is the formula for any molecule. So anytime I write down a molecule's formula, that's the molecular formula. The empirical formula is the lowest ratioed of that possible formula. So if I gave you an example, it would look something like this. And if I were to go, all right, so I have NO, no. And I have N2O2, and I have N3O3. Clearly, these are all exactly the same ratio, right? These are all molecular formulas, but only this one right here is the empirical formula because you cannot reduce it any farther. So what they'll often do in a problem is they'll give you the percentages, and then they'll say, oh, by the way, the molecule we're looking for has a particular molar mass, like they do right here. Now, what you need to be aware of is this. Each of these compounds right here, they have exactly the same ratio of nitrogens to oxygen. In fact, the percentages of both nitrogen to oxygen in all of these compounds is going to be identical. So in order to figure out, hey, the formula they're looking for is this one right here, what we have to do is we have to figure out the empirical formula first and then compare it to the molar mass they've given us and see which molar mass matches up for each of these. Now, I'm going to go kind of quickly through this because you guys have it in your notes, but if you take a look down here, they give us 4 different percentages, because why not, right? And they give us the molar mass of caffeine of 194.2. So our job is simply this. If we can figure out the empirical formula for this right here, right, and then figure out its molar mass, we can then compare it to the molar mass that they've given us and determine whether or not the compound we have is the empirical formula or not. For example, before we even do this problem, see how the number they're looking for here has the molar mass we're looking for in the compound is 194.2, right? If we were to divide that by 2, right, wouldn't that give us 96.1 grams per mole, right? So let's say, I'm not saying this is going to be the case, but let's say we did the empirical formula and we got the empirical formula and the molar mass of the empirical formula was 96.1. We could then compare it to 194.2 and go, oh, wait, actually, I think I did that wrong. I think that's actually 197. Sorry, it's late. I could go, all right, if I divide 97.2 into 194.2, this is 2 times bigger than this. So whatever my empirical formula is, I'd have to multiply it by 2 to get to this formula, and that's what our molecular formula would be. So we're going to hit 3 sections right in a row really quickly right now because this is stuff that you have done before and you understand. But they put it in here because they want to, make sure that you at least have been exposed to it. We're aware that when we have reactions, they form products, and the number of atoms on each side have to be equivalent to the number of atoms on the other side because of the law of conservation of matter. Now they've gone ahead and they've shown you how this works with atoms themselves, and clearly this here is not balanced, but if you take 2 of these compounds, it balances off, and the number of atoms on this side have to equal the number of atoms on the other side. Now this may seem simplistic to you here, but it is really, really important because we're going to be able to solve some pretty high-end problems just by understanding the fact that the number of atoms you have at the beginning has to always be equal to the number of atoms you have at the end. There's a little video here that you guys can watch on this. I encourage you to do so. Let's move right on to the meaning of a chemical equation. You guys should know this already, but now we're gonna emphasize it a little bit more. Solid, liquid, gas, and aqueous. These 4 things right here. It's really, really important that you include those as part of your equations because sometimes things act differently when they are gas versus when they're solid, aqueous, etc. Secondly, the coefficients matter. Like we already know they matter, but they can be referring to molecules, they can be referring to moles, they can be referring to all kinds of things. Now you have to be careful though. When you see the numbers in front of you here, the 1 to 1 to 1 to 1 ratio, or the 1 to 2 to 1 to 2 ratio here, these coefficients, they are not gram ratios. If you see what they did right here, they put in parentheses the number of grams per 1 mole of that thing. But don't you ever think that you can put grams as in the place of coefficients. Now, there's really not very much more with this here, but the last thing I want to talk to you about here is balancing equations. Now, this can actually end up being pretty tricky. We know this already. You can only mess with the numbers or coefficients. You cannot mess with any of the numbers that are part of the overall compounds. Now, it is really, really smart to leave the hydrogens and the oxygens to the very end. You also want to make sure that you are leaving the you also want to make sure that you're leaving things that appear twice on one side to the very end as well, because hopefully they'll work themselves out. Unfortunately, we do this thing called balancing by inspection, which is essentially trial and error. I would walk through this just to remind yourself how to balance these things. They kind of walk you through these steps here. I'm not going to go in depth with this here, but you should practice doing some of these, and I'm going to kind of force you to do it because you need to balance these equations. Now, once you balance these equations, we can then use those equations, the coefficients, to actually help us solve problems. In other words, if I have a balanced equation, right, and let's say here I have a 2 to 1 ratio, if I know how many moles of NH3 I have, I know that for every 2 moles of NH3, I'm going to need 1 mole of O2. So this is kind of helpful to realize that we are going to be using these as we move forward. Now we're almost about getting ready to use equations, but I'm going to put a pause right here for this video. Thanks, guys. I'll see you soon.